Hello, how are we? Cortez Morales, Josue Yair, and Munoz Sandoval. Brandon Josue, and today we will show you what the conjugate beam method consists of. Introduction. A conjugate beam is a fundamental concept in structural analysis and is used to simplify the study of loads and reactions in beams. In a conjugate beam, the applied loads and reactions at the supports are considered to be distributed along the length of the beam rather than concentrated at specific points. This simplified approach facilitates structural analysis by allowing the application of more direct and efficient mathematical methods. Conjugate beam theory is especially useful in determining internal forces, such as bending moments and shear forces, in different sections of a beam. Importance in structural engineering. The importance of conjugate beam theory in structural engineering lies in its ability to simplify the analysis and design of structures. 1. Simplification of analysis. The conjugate beam provides a simplified method to address structural problems, allowing the use of simpler and more direct equations. 2. Design efficiency. By using conjugate beam theory, engineers can quickly determine the internal forces and moments in different sections of a beam. 3. Widespread application. The theory of conjugate beams is applicable to a wide variety of structures and settings, from bridges to buildings. 4. Intuitive understanding. The representation of loads distributed along the beam facilitates the visualization and intuitive understanding of how the forces act in different sections. 5. Saving time and resources. By simplifying the analysis, conjugate beam theory allows engineers to save time and resources compared to more complex methods. Definition: conjugate beams are a simplified representation of a beam in structural engineering, where the applied loads and reactions at the supports are distributed along the length of the beam rather than concentrating at specific points. Use of more direct mathemos. Relationship between the applied loads and how they affect the beam. The relationship between the applied loads and their effect on the beam is interpreted through the distribution of forces along the length of the beam. 1. Load distribution. In a conjugate beam, the applied loads are considered to be distributed uniformly along the length of the beam rather than concentrated at specific points. 2. Effect on the beam. The distribution of loads in a conjugate beam has a direct impact on the internal forces and moments along the beam. 3. Beam balance. The beam is still in equilibrium and the reactions at the supports remain the same, but the approach to the analysis is more convenient when considering distributed loads. Key features of the conjugate beam method. Some more notable features. 1. Uniform load distribution. In a conjugate beam, the applied loads and reactions at the supports are distributed uniformly along the length of the beam. Or 2. Constant shear force. Throughout a cross-section of a conjugate beam, the shear force is constant. This means that the uniform distribution of loads results in a shear force that does not vary along the length of the beam. 3. Constant bending moment. Similar to the shear force, the bending moment along a cross-section of a conjugate beam is constant. This facilitates the calculation and analysis of internal forces. 4. Facilitates the section method. The theory of conjugate beams is particularly useful for applying the method of sections. This method involves cutting the beam into sections and analyzing the internal forces in each section, and the uniform distribution of loads simplifies this process. 5. Clear visualization of internal forces. Graphical representation of conjugate beams provides a clear and intuitive visualization of how internal forces, such as shear force and bending moment, vary along the length of the beam. 6. Simplification of mathematical analysis. The uniform distribution of loads simplifies the mathematical analysis of internal forces, allowing the use of simpler and more direct equations compared to more complex methods. 7. Application in continuous beams. Conjugate beams are especially useful in the analysis of continuous beams, where the uniform distribution of loads facilitates the study of internal forces in different segments of the beam. Analysis methods, sections. Method, concept. This method involves cutting the beam into cross-sections and analysing the internal forces in each section. It is mainly applied to beams in static equilibrium. Steps. Select a section of the beam where you want to know the internal forces. Make an imaginary cut in that section and isolate the part of the beam that is being analysed. Apply the equilibrium equations and loading relationships to determine the internal forces, such as shear force and bending moment, in the selected section. Repeat these steps for different sections along the beam to get a complete representation of the internal forces. Area method concept. The area method is based on the graphical interpretation of the areas under the load and moment curves. It is used to quickly obtain the magnitudes of internal forces. Steps. Graphically represent the applied loads and moments along the length of the beam on a load-moment diagram. Identify the areas under the curves on the load and moment diagram. The areas represent specific magnitudes of internal forces. The area under the load curve indicates the change in shear force, and the area under the moment curve indicates the change in bending moment. Add or subtract the areas to obtain the final shear force and bending moment values at specific points along the beam. Conclusion. In conclusion, conjugate beams are an invaluable tool in the field of structural engineering, offering a simplified and efficient way to analyze and design structures. Its ability to consider loads distributed uniformly along the length of the beam significantly simplifies the analysis, facilitating the use of simpler. Conjugate beams provide a clear and intuitive visualization of internal forces, such as shear force and bending moment, allowing engineers to make informed decisions about the design of structures efficiently and accurately. For the development of this cantilever beam, we will apply the conjugate life method. In the exercise, we are asked to calculate the deflections at the point of I did as shown in the figure. By the principle of superposition of loads, we say that the real beam is equal to the first beam plus the second beam. Then adding forces in and calculating the reactions in A and D. Now we will graph the moment diagram, knowing what moment is equal to the force times the distance developing. We have 40 times 2 meters, which is equal to 80, as shown in the figure. We do the same for the next beam, 50 times 2 meters, which is equal to 100. Then we join the two diagrams and conjugate the beam. In the following way, we know that a cantilever beam in real life is equal to a built-in conjugate beam, and an intermediate support in real life is equal to a hinge in the conjugate beam, as shown in the figure. Then we calculate the resulting forces for each section and also the moments in D and C. Now we calculate the reactions for section AB, we add the moments in B, developing, we have that reaction in A is equal to minus 13.333 tons on EI, and by adding forces in Y, we obtain that the reaction in B is equal to 53.333 tons on EI. And finally, we locate the reactions. Now we will calculate the deflection at D. For that we make the cut at point D, then we add the moments at D where counterclockwise is positive. Developing, we have that the moment at point D is equal to minus 6.666 tons per meter on EI, knowing that the moment at the conjugate beam is equal to the reflection in real life. So the reflection at D is equal to minus 6.666 tons per meter over EI. Finally, we will calculate the slope and the deflection in C. To find the slope in C, we make the sum of forces in Y is equal to 0. Developing, we have that the reaction in C is equal to 153.333 tons on EI. Now we know that the shear in the conjugate beam is equal to the slope in real life. Then the slope at C is equal to 153.333 tons above EI. For the deflection, we add the moments at C developing. We have that the moment at C is equal to minus 239.999 tons per meter above EI, knowing that the moment in conjugate life is equal to the reflection in real life. So the deflection at C is equal to minus 239.9999 tons per meter above EI. Finally, here we have the graphic representation of the deflection of the beam where the values are shown at point D and C. Well, thank you for your attention. I hope the exercise using the conjugate beam method has been useful to you.